Madame la directrice générale du
This is Director General of CERN, ladies and gentlemen, representatives of the State Council, ladies and gentlemen, representatives of international organizations, students, colleagues. It is a pleasure for me to welcome you this evening for the opening of the fall semester 2017-2018. You are 1,200 people attending this conference to open the fall semester this evening. So this is a great success which proves the interest of the public in Geneva for science and more specifically for the University of Geneva. This conference is a pleasure for me in many respects. It is an emblematic one. It is proof of a series of developments we have tried to support within our university. First, with strong relationships with CERN and more generally with other international organizations. You are fully aware of those relationships which have been established with the Faculty of Science in the field of particle physics and material physics, as well as with the Faculty of Medicine. And I met with one colleague from this faculty who said that he decided to join it because of the presence of CERN, because CERN will help us have the necessary isotopes for the research we are carrying out. So this is the type of strong relationship that we are trying to establish with other international organizations. I signed a convention with the Federal Council, Mr. Bulcarter, last week. So we signed this convention in the field of water governance, which is another example of the type of relationship we want to establish with international organizations in the fields for which we have strong competences. And this is why we wish to launch an interface between the academia and the DFA. This is a platform that would deal with a variety of topics linked with our university and international organizations. So I am pleased to welcome you at this conference because it shows that behind innovations and new developments, you always find fundamental research, hence the importance of our relationship with CERN. And I'm pleased to note the ranking that was published this summer. I'm sure you're aware of it. It was established on the basis of the number of patents that were filed over the last few years. Those patents were analyzed and examined in order to find out which type of research helped come up with those patents. And our university ranks 21st. It is the third institution outside of the United States, just behind the University of Strasbourg. So we rank 21st. It's a great pride for us and for all of our researchers and scientists who are carrying out all this research. So innovation also concerns other fields such as teaching. I will not take up too much of the time dedicated to Mrs. Gianotti's talk, but a number of initiatives are planned for this fall. We have a master regarding sustainable development, which will start in September 2017. There's also a master on biomedical sciences. And a large number of young people are interested and wish to study the field of science and medicine, and the idea was to meet the expectations and the requirements of the industry. So innovation in the field of teaching is also of importance to us. I could mention another field of study in business analytics. So as you can see, innovation is at the heart of our development, and this is something we wish to pursue further in the future. in light of the difficulties we're having regarding our budget, we are making the best we can to keep up the level we've reached. I would like to conclude this brief intervention to thank you for being here and to draw your attention to a conference that will be held in September. It is organized by CERN, and it is the 13th European Conference on Applied Superconductivity from the 17th to the 21st of September. And I think there will be an even larger number of participants, which shows that everything CERN does is of interest to many people, and you will be able to appreciate this via the conference of the Director General that we are going to hear right now. So thank you for your attendance, and I wish you a great evening with the Director General. But first of all, I will give the floor to the Dean of the Faculty of Science, who will give us a brief introduction. Thank you.
Mesdames, Messieurs, c'est un vrai plaisir, vraiment.
Ladies and gentlemen, it is with great pleasure that I am taking up the task of introducing you to Dr. Fabiola Gianotti, who holds a PhD from the University of Milan in the field of experimental particle physics. She's been working as a physicist since 1994 within the physics department of the European Organization for Nuclear Research, CERN, and she is also honorary professor at the University of Edinburgh and a member of the Italian Academy of Sciences. Fabiola Gianotti worked on a number of CERN experiments and took part in R&D work as well as sensor and software development and data analysis. In March 2009, she was elected as chief of project. I think she doesn't really like this name. She prefers to be named as a spokesperson. She held that position until February 2013. And the Atlas collaboration comprises 3,000 physicists from 38 countries. And Fabiola Gianotti introduced the results of the Atlas experiment in July 2012 with a major discovery, which is this evening's topic. So her colleagues describe her as an expert in her field, of course, and as someone who knows a lot of other experts to which she never hesitates to refer to. It's a very important point. She has a great sense of organization, and she has very good relationships with other physicists, and she sees to it that results should be made public in a punctual way, and her publications have been written without much controversy, and everything has been working like a Swiss clockwork with no problem at all. And Fabiola Gianotti is the author of over 500 scientific publications. She was invited to present in over 30 plenary sessions of major international organizations. She's the member of several international committees, such as the CNRS or the Fermilab Consultative Committee in the US. She's also a scientific consultant to the Secretary General of the UN. She also obtained the title of Grande Ufficiale dell'Ordine al Merito della Repubblica and earned a special prize, the Enrico Fermi Prize in 2013, the Medal of Honor of the Institute Niels Bohr Institute in Copenhagen. So many titles. In 2011, the Guardian newspaper ranked her among the 100 most inspiring women in 2012. Time magazine ranked her 5th personality of the year, and Forbes ranked her among the 100 most influent women in foreign policy, ranked her as one of the greatest thinkers of the planet for 2013.
Enfin, depuis 2016, elle est...
And since 2016, she's the very first female to be Director General of CERN. So I invite you to join me. We can't wait to hear your thoughts on the Higgs boson.
Merci beaucoup. Bonsoir tout le monde. Je me réjouis d'être ici ce soir.
Thank you. It's a pleasure for me to be here with you this evening on the occasion of the fall semester opening lecture and the European Conference on Applied Superconductivity. I would like to thank the Dean and those who took the floor to introduce me. So I will switch to English for my presentation because there are many attendants who do not speak French with us this evening. Of course, I would be willing to take your questions later on in French after my presentation.
The first slide. Okay. So I'm very pleased and honored to be here, and I would like to thank the director, Professor Flugiker, and the organizer of the UCAS 2017 conference for the invitation to give this lecture. I think you have all heard about CERN at least once in your life, and perhaps some of you also heard about the Higgs particle, about the Higgs boson. Tonight I would like to address these two topics from a slightly different viewpoint, not only the scientific perspective in simple words, but also I would like to emphasize the impact of what we do at CERN and of the discovery of the Higgs boson on our life. So first of all, I would like to remind you that CERN is the largest laboratory for particle physics in the world. From the legal point of view, it's an intergovernmental organization based in Geneva. Its primary mission is science. We do fundamental research in particle physics, and particle physics is the most fundamental of all sciences because it really studies the building blocks of matter, the smallest particles of which the matter around us and the universe is made. And these researches have been awarded by many discoveries. The last one is the Higgs boson, and Nobel Prizes awarded to scientists working at CERN. Our scientific goals actually require the development of very complex and sophisticated instruments in three main domains: particle accelerators, particle detectors, and computing infrastructures, and so require us to really to push the limits of technology. And these technologies are transferred to society. Everybody knows that the World Wide Web was invented at CERN simply to facilitate the exchange of information among the scientists. And then, of course, it has been transferred to society, and since then it has changed the way people access information. And I will give you more examples in the course of this presentation. Another important element of our mission is training and education. Of course, tomorrow's scientists, physicists, engineers, technicians, but also high school teachers and high school students through several initiatives that I will mention briefly later on. And CERN is also a fantastic place to foster peaceful collaborations by attracting about 17,000 scientists from all over the world, more than 110 different nationalities. CERN was founded in 1954. This is the only historical slide I have, so don't be afraid, by 12 European countries with the twofold goal of reestablishing scientific excellence in Europe after the war and also fostering peaceful collaboration among European countries again after the disaster of the war. Today, CERN has 22 member states, also from outside Europe, like Israel, and 7 associate member states. The budget is 1.1 billion, about 1.1 billion Swiss franc a year. And I like to use another unit. So 1.1 billion Swiss franc per year correspond on average to 1 cappuccino per European citizen per year. This is the contribution of Europe to CERN. I said on average because you all know that the cappuccino is very cheap and tasty in Southern Europe. Then you move toward Northern Europe and it becomes expensive and okay. So the budget is shared by the member state countries in proportion to their net national income. So the largest contributor is Germany, followed by UK, France, Italy, and so on and so forth. And Switzerland contributes about 4% of the budget, namely 44 million Swiss francs. Now, this budget is used to develop, build, maintain, upgrade the infrastructure like accelerators, laboratories, workshops that are used by the worldwide communities of high-energy physicists, particle physicists, to do research at CERN. And this community is very, very large. I told you before, we have in total 17,000 people, of which 13,000 come from outside CERN. And you see here the map of all the CERN users. In blue, you see in dark blue, you see the member state users from the member state countries, here in blue. But you see that another half comes from all over the world. So we have physicists coming from Zimbabwe, from Azerbaijan, from Ecuador, from Senegal. And some of these physicists come from countries which are at war with each other, or even countries that do not recognize each other the right to existence. And yet, at CERN, they work together, animated by the same passion for science, for knowledge, because knowledge is a universal value that transcends the interest, the political interest of countries, or the different beliefs, or the diversity in terms of ethnicity, etc., etc. So if you think that all these scientists here are a bit old and a bit boring, you are wrong. Because if you look at the age profile of these users from all over the world, mainly physicists, you see that the peak is at 27 years old. Of course, I am here in the peak. It's not nice, huh? Okay. Now, not all, so these young people, 27 years old, around that means most of the people are young students or young postdoc. Of course, they do not all remain in the field. Typically, because they want to change, or because also, of course, the positions and the jobs offered by the field are limited. So typically, 10% of them remain in the field, and the other 90% go elsewhere. So where do they go? Typically, 0.5% goes to remain in the public sector, universities, research in other fields, and half of them go to the private sector, industry. So communication, engineering, physics, but also finance. And a recent survey shows that more than 97% of the young people who left the field, who left CERN, had no problem to find a satisfactory job, meaning that the education they receive allows them then to have strong CVs and therefore to find a job, which is already today is already not obvious, but also a job at the level of their talents and their expectation, which I think is very good. So because we have so many young people and because it's part of our mission, educational activities are really a core part of what we do at CERN. So we have, of course, schools for people in the field. So PhD student and young postdoc, physicists, engineers, and also technician, on topics like accelerator, particle physics, computing, etc. And these schools actually started, the physics school in particular, started in Europe in 1960, and since then it's taking place every year in Europe. But then, a few years ago, we started also to move the school every second year to Latin America. So we have been in Mexico this year, in Ecuador two years ago. We then moved to Asia, and recently, since 2010, we are also co-organizing schools in Africa. So we've been in South Africa, Ghana, Senegal, Rwanda, etc., in order to foster capacity building and building capacity in those countries. We also have initiative for high school students who try to attract high school students to STEM, so science, technology, engineering, and maths, and also for high school teachers. So high school teachers typically come to CERN a couple of weeks during the summer, and they receive a complement of training, of education, with hands-on physics. And this program has been going on for about 15 years, and since then we have formed, educated, trained more than 10,000 high school teachers. And every year we welcome 120,000 visitors. 60% of them, more than 60% of them, are high school kids, and we receive at least 3 times as many requests that we cannot accommodate. We receive typically 350,000 requests a year, and we can only accommodate 120,000 of them. So, CERN primary mission is science. What we do at CERN, we study the elementary particles. Elementary means that these particles cannot be cut into smaller pieces. And among those elementary particles, we can include the building blocks of matter. And we study the forces that act on these particles. So I think we all know today that matter is made of atoms. Atoms are made of a central nucleus and surrounded by a cloud of electrons. And the nucleus, in turn, is made of protons and neutrons are made of smaller particles called the quarks, bound together by other elementary particles called gluons. And as far as we know today, quarks and electrons are elementary particles. They cannot be cut into smaller pieces, and so they are the building blocks of matter. So the matter, ordinary matter, of which we are all made, myself, this laser pointer, this desk, even the rector of the university, Professor Flugiger, we are all made of electrons and quarks. Now, physics are modern accelerators, and the most powerful accelerator ever built by mankind is the Large Hadron Collider here at CERN, allow us to scrutinize and study matters at the level of the quarks or below. And on the physical size, this corresponds to 1 billionth of a billionth of a meter, so 10 to the minus 18 meters. So these accelerators can be seen, in some sense, can be assimilated to giant microscopes that allow us to study not the cells, as in biology, but something much smaller than the cells, so the elementary particles. So at the same time, the study of the infinitely small, the elementary particles, allow us to understand the infinitely big, so the structure and the evolution of the universe. And the reason is that we know today from cosmology, but also from a set of very precise experimental measurements, that the universe had origin about 14 billion years ago from a big explosion, so-called Big Bang. And at the beginning, it was very hot and dense, and it was made of elementary particles, free elementary particles. So by studying the elementary particles and their behaviors in the lab at CERN, in another laboratory, we can understand how the initial universe behaved. With time, the universe cooled down, and so the elementary particles started to get together to form first the quarks and the gluons, to form the neutrons and protons, and then the nuclei to form together with electrons to form atoms, and then molecules, and then so on and so forth, the macrostructure that we know today, stars, planets, galaxies, etc. And there are 2 complementary ways of studying the universe. One is through a telescope. The telescope looks at the macrostructure, galaxies, planets, etc., and they're trying to go back and to reconstruct the history of the universe. However, there is a kind of hard wall beyond which they cannot go. This corresponds to 380,000 years after the Big Bang. So at earlier epoch, the light to which these telescopes are sensitive, they detect the light was trapped in this gas of elementary particles. It could not escape, and so it never reached us. And so the universe was opaque, and telescopes cannot go back to earlier epochs than 380,000 years after the Big Bang. So to study these very early epochs, the thing that we can do is to use mainly accelerators. There are perhaps other methods, but accelerators are the main tool. So how do we do this in practice? I'm not going to be very rigorous, so I hope that what I'm going to say stays here in our small room among the few of us, that my colleagues can physicists can sleep for a couple of minutes. And so what we do, we accelerate two beams of particles, so two beams of protons at the highest achievable energies, and we'll see later on what it means. And then we bring them, we smash them, we bring them into collisions. And to do so, we use accelerators. Accelerators are devices essentially containing electric field and magnetic field, usually housed in underground rings. You can see here, for instance, this nice picture, the underground tunnel of the Large Hadron Collider. When the two beams are brought into collision, many things can happen. So you have two protons, one proton from one beam and another proton from another beam, accelerated at the largest, at the highest achievable energy, and they smash. So they smash, and what do they do? Well, they break into, so to speak, it's not scientifically rigorous, they break into thousands of pieces. Like when you drive two cars at very high speed, you drive your Ferrari at the highest possible speed against the Ferrari of your neighbors, and the higher the speed, the more the cars break into thousands of pieces. So you can understand how they are made and the pieces of which they are made. In a similar way, we try to break the protons to understand how the quarks and the gluons that are the fundamental constituents behave. At the same time, the energy produced in the collisions can transform itself into new particles, and the higher the energy of the collision, the more massive the produced particle can be. So that's why particles that have not been observed at previous accelerator have been discovered more recently. So the Higgs boson, for instance, has been hunted for almost more than 30 years and has been finally found at CERN because only the Large Hadron Collider had enough energy to produce the Higgs boson with sizable rate. So to detect the product of the collision, what we do, we surround the collision region with instruments called particle detectors. These are cylinders, concentric cylinders, closed at the two ends by what we call end caps, and these cylinders are made of different materials, silicon, scintillator, noble gases, etc. And their task is to detect, ideally, every single particle that is produced in the collision, measure the trajectory of every single particle, and there are thousands of them produced in each collision, so measure the energy, identify every single particle, and therefore giving a kind of picture of the collision event. So if accelerator can be assimilated to microscopes, particle detectors can be assimilated to giant digital camera, which have to, which take pictures of the event. The problem is that the two beams of protons at the LHC collide 40 million times a second. So these detectors have to be able to take pictures 40 million times a second. Not all these pictures are stored because it would be impossible to analyze them, only a fraction of them, but nevertheless they have to be able to process the signals coming from this collision very, very quickly. Now, the most powerful accelerator ever built by mankind, as I said before, is the Large Hadron Collider. At CERN is a 27-kilometer ring, 100 meters underground, and for those of you who are not familiar with the region, this is an aerial view of the region we live in, and you can see here on the background the Alps, you can see Lake Geneva. The dashed white line shows the border between Switzerland on the top and France here. Here are CERN headquarters, and this yellow ring indicates the position of the Large Hadron Collider, 27 kilometers, 100 meters underground, so you don't see much on the surface, but then if you come and visit CERN in some periods of the year, you can go down and see the tunnel, and you can see also the experimental detectors. So operation started in 2010, and at the time we started to circulate and since then actually, two beams of protons have been circulated in the two opposite directions at the highest possible energy and brought into collision at 4 points of the accelerator, where 4 big experiments called ATLAS, CMS, ALICE, and LHCb have been installed in gigantic underground caverns, and they detect the products of the collisions. And only a couple of years later, after switching on the collider, Atlas and CMS announced the discovery of a new particle, a very special particle called the Higgs boson. Higgs after Peter Higgs, one of the scientists who have predicted this particle. I will come to this later. And boson indicate a class of particles which have some special features, and is after an Indian physicist named Nath Bose. I would like to stress that the University of Geneva has contributed in a very significant way to the construction, development, construction, operation, and now upgrade of the Atlas detector, and also to the data analysis and to the discovery of the Higgs boson really on the front line, with a group of about 40 scientists, engineers, physicists, including 13 PhD students, so it's a young group. So the LHC, in all its components, accelerator, detectors, computing, and also perhaps worldwide international community, is one of the most extraordinary and complex projects ever realized by humanity. And it has required the development of new concepts and technologies, entailing, of course, risks. When you explore new territory, not only in physics, but also in technology, you take risks, calculated risks, but we went through years of great difficulties, and the efforts of the worldwide scientific community of the field. So I will give you a couple of examples. So this spectacular picture shows the LHC underground tunnel. These blue tubes contain a set of 1,232 superconducting magnets, and these superconducting magnets, new generation at the time, and today still are really the best we can do for a big accelerator. These magnets are perhaps the most important single ingredient that has allowed us to make a big jump in energy compared to the previous colliders. Because in a proton accelerator, what is difficult is not to accelerate the protons. This is quite easy. What is difficult is to bend the proton and to confine them in a ring. It's like when you drive, again, your Ferrari, before you collapse with your neighbor. You drive your Ferrari, and if you are in a closed circuit, the higher the speed of your car, the more difficult it is to keep it on track. Similarly here, if you accelerate protons at the largest, at the highest energies, and then to keep them on the ring, inside the ring, we need very strong magnetic field to bend them and to guide them then, of course, also in collision. So high magnetic fields require high current. We are talking about 12,000 ampere. And high currents can, in practice, be achieved, such a high current, only with special materials called superconductors. These materials are such that when cooled down at temperature below a critical temperature, they have no resistance. So they can carry very, very high current seamlessly without any resistance. And so for the LHC, we have been developing new generation superconducting magnets based on a material called niobium titanium. These magnets work in a bath of about 120 tons of superfluid helium at a temperature of 1.9 Kelvin, cold temperature because of the reason I explained before. Superconducting magnets have to be brought to lower temperature. 1.9 Kelvin is 2 degrees from absolute zero, means minus 271 degrees, and we use to say that the LHC is the coldest place of the universe. The reason being that, as I mentioned before, the universe had origin from this big explosion and then it cooled down. And if you ask yourself, or me, what is the temperature of the universe today? The average temperature is 3 Kelvin, and the LHC works at 1.9 Kelvin. So we see we are the coldest place in the universe, but also the coolest place in the universe. Anyway, thank you. My colleagues are happy, of course. Okay, so these magnets are used to bend and to bring into collision beams of protons, and in each beam of protons, when we operate the collider at full power, we have something like 200,000 billions of protons circulating in the two directions, making something like 11,000 turns of the accelerator per second and colliding 40 million times a second in the LHC experiment. So it's quite challenging. The experiments are also quite challenging. So this is also, again, a spectacular view of Atlas, which is the biggest, one of the 4 experiments. So you can see the size compared to 2 human beings. I can assure you these two human beings are of average size. They're not particularly small. So you can appreciate. It's Atlas is half Notre Dame. The other experiment, CMS, has more iron than the Tour Eiffel, to remain in Paris, and weighs twice as much as the Tour Eiffel. So what clearly impress people and visitors when they come and go down in the experimental cover is the size, which is really breathtaking. And you are, of course, all invited to come and to visit. But these experiments are also extremely precise. Their core is made of about 100 million sensitive elements that are used to reconstruct the trajectory of every single particle, as I mentioned before, with micrometric precision. A micron is a millionth of a meter, so that they can really reconstruct with very, very high precision these thousands of particles produced in the collision. You can see here the insertion of the innermost layer of the Atlas detector. This layer is just at 3.5 centimeters from the beam line and is made of 6 million high-tech silicon sensor of size 50 microns times 250 microns. And the University of Geneva has made very, very strong, important contribution to the construction, in particular, of this device. So to extract the signals from the detector and to bring them to the surface rooms where they are stored, we need 3,000 kilometers of cables. You can imagine the nightmare of all these cables. And every year, each one of the 4 LHC experiments produce something like 10 petabytes of data. So typically 50 petabytes of data in total. If you wanted to write this data on conventional DVD, you will need 20 million of them, or a pile, 20 kilometer high pile. So clearly the question is why? So why did we decide to embark in this absolutely fantastic but also very challenging adventure? And the reason is that, well, the LHC has been conceived, developed, and built in order to address some outstanding questions in fundamental physics. Question number 1, and I will then elaborate it a little bit more, is what is the origin of the masses of the elementary particles? I will come back to this later. And now we have answered this question, at least in large part, with the discovery of the Higgs boson. So this question is in large part ticked off. But there are other open questions that we are addressing now. A very important one which is very important and actually is focusing the interest of not only the particle physics community but also of the astroparticle community is the fact that when you look at the sky overnight and you see the beautiful stars, galaxies, planets, etc., what you see is only 5% of what is out there. The rest, 95%, is question mark, is what we call the dark universe. 95% of the universe is made of form of matter and energy that we don't know, and we call them dark matter and dark energy. Dark indicates A, our ignorance, and B, that this form of matter and energy do not interact with our instruments. So you will ask, okay, but how do you know they are there? Well, we have indirect observation that very precise now, and several indirect observations, not just one, that point out to the fact, for instance, that in the universe we have 25% of dark matter. We don't know the composition of dark matter. We don't know what particles it's made of. But if it is made of some classes of particles, we may be able to produce them at the Large Hadron Collider in the collision of the proton beams. And of course, it will be a triumph for science if we were able to produce the particle that explain 25% of the universe in an accelerator underground here in the Geneva region. But of course, we don't know. And there are many other approaches, experimental approaches, to look for dark matter. Another important question is that why the universe is essentially only made of matter. Where did the antimatter go? Antimatter, although people are scared by the name antimatter, antimatter is as nice and as friendly as matter. And we know that when the universe was born after the Big Bang, we think that matter and antimatter were present in the early universe in same proportion. But then at some point, some asymmetry came into the game, and the antimatter disappeared. And today we live in a universe fully made of matter. We can produce antimatter artificially. We do also so at CERN every day. We have a dedicated antimatter facility, but we have to synthesize it. It doesn't exist in a free state. So we cannot explain why it is so, and so on and so forth. So in 2012, we discovered this particle, special particle called the Higgs boson. It's a monumental discovery in fundamental physics, because before the discovery of this particle, we didn't know how the elementary particles get their mass. So why, for instance, the photons that we all know, this room is full of photons, they are the quantum of lights, are massless, and they fly and they run at the speed of light. And other particles, like the W particle, which was also discovered at CERN in 1982, 1983, which is responsible for radioactive decays or the thermonuclear reaction in the sun. The W particle is massive, has a mass 80 times the hydrogen atom. At the beginning of the 60s, a group of scientists, physicists, among which Robert Brout, François Englert, and Peter Higgs, developed a theory, a mechanism, which would allow some particles, like the photon, to remain massless, and the other particles to acquire a mass. And one of the consequences of the theory was the prediction of the existence of a new particle called the Higgs boson, which has been hunted since then at accelerators and laboratories all over the world, and was only discovered at CERN in 2012, because only the LHC had the energy to produce it. I will not go into the details of this Higgs mechanism and how it works. I will be happy to answer questions. But I can imagine that now, at this point, your main question is, who cares about the Higgs boson, the particle masses, etc.? And you should be caring about it, because if the electron and the quarks that we have seen are being the fundamental constituent of atoms did not have a mass, atoms will not stick together. So the ordinary matter of which we are all made will not exist. We will not be here. Perhaps there will be another universe. We don't know. But we are what we are because the elementary particles have exactly the masses they have. And the Higgs boson is a first step to understand how this happened. So this is the first link of the Higgs boson to our life. Of course, all other elementary particles are important. It's not that the Higgs boson is more important than others, but it has a very special, it plays a very special role in the zoo of the elementary particles. Then 1 year later, the Nobel Prize in Physics was awarded jointly to the two theorists, François Englert and Peter Higgs, who had postulated the existence of this particle in the early 60s. Robert Brout, unfortunately, passed away before that. And in the motivation of the Swedish Academy of Science, of course, is the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, confirmed through the discovery of the predicted fundamental particle by ATLAS and CMS at the Large Hadron Collider. So the importance of what we do at CERN has been recognized. And for the expert in the audience, these diagrams here show the signal of the Higgs boson as we observed them at the beginning of July 2012, at the time of the announcement of the discovery. So you see here the Higgs boson has been observed in 2 decay mode. This is produced and it disintegrates itself immediately. It decays in 2 photons. You see here the peak on top of the background, and after background subtraction, this is the signal of the Higgs boson, or can also decay into 4 leptons, electrons, and muons, and this is the nice peak. So I close the parenthesis for the expert. And I go to the next link to our life. So perhaps the most common question that people ask me, actually this is the second most common question. The first question is, how do you feel being the first female Director General of CERN? So after I've told them how do I feel being the first female, the next question is, will the Higgs boson change our life? And my answer is, it already has. Because, as I mentioned before, in order to find these tiny particles, we had to develop and to build very complex and fantastic, extraordinary instrument, accelerator, detector computings, and push really the technology and our knowledge in many fields, from cryogenics to superconducting magnets, material to electronics, fast, radiation hard, and very high resolution electronics, computing, software, etc. And all these technologies are available for free for society. So I mentioned the web at the beginning, but the work at CERN has also had impact on material science, on solar panels. And I would like perhaps to give 3 specific examples. Today we have something like 30,000 particle accelerators worldwide. Only perhaps a dozen of them, or 2 dozens of them, are used in fundamental research at CERN and other similar laboratories. Most of them are used for other applications, material science, and a big fraction of them, about 17,000, are used in medical applications. One of these applications is what we call Hadron therapy, and consists in bombarding tumoral tissue with protons, and this is, or light ions like carbon ions, and this is a therapy which is complementary to the more traditional radiation X-ray therapy. And the advantage of this, of protons, is that they are extremely focused. So if you bombard the tumor, you really hit only the tumor and not the surrounding tissue, whereas with radiation, the radiation expands over a larger area. Another example of application of CERN technologies, the PET scanner, which is perhaps the main diagnostic technique used, for instance, for cancer, is based on detectors and instrumentation developed at CERN. And last but not least, superconductivity, which is the topic of this UCAS conference, organized jointly by the Université de Genève, the Swiss Plasma Center in the EPFL and CERN. This picture illustrates for the non-expert the power of superconducting material. You see this little thin cable based on this material, niobium titanium, is the cable that we use for the LHC superconducting magnets that I showed before, and it can carry a current equivalent to this bundle of normal conducting copper wire. So you see the difference. You can bring very high current with very small cables. So also in this case, CERN and other laboratories in the world of the field, high energy physics, have been really driving also the applications to other fields like fusion energy, because now superconducting magnets, for instance, are used in the ITER project in Cadarache, or also again application to the medicine through the MRI, magnetic resonance imaging. We have been leading also the industrialization, because we need to build these enormous big accelerators, and so we have not only to develop superconductors with the right features, but we also have to make sure that they can be built by industry, and magnets can fill 27 kilometers or so. And for us, it's a need. We cannot really advance the discipline without accelerator, and so without superconducting magnets. And this is the second link to our life. The fact that the technologies we develop go to the advantage of everybody's life. So this shows that fundamental research is a driver of innovation, and I would like to finish with a few words in support of fundamental research, because ideas and creativity are clearly the fuel of progress. History shows that progress evolves smoothly, but then at some point you need a breakthrough. You need what we call a breakthrough, or a revolutionary idea, to make a big step. So the example that very often we give is the light in this room is not just the evolution of a candle. It's not that by building bigger and bigger and more colorful and exotic candles, you get this light. This light is the result of a jump in our knowledge in fundamental physics and in fundamental science. And so history also shows that fundamental research is the one that most stimulates these ideas and creativity. The reason is very simple, that fundamental research has no constraints from delivering a specific product. Applied research is also very important. Research in industry is also very important, but it has some constraints from time, delivering a product, economical return, etc. On the other hand, fundamental research really leaves the researchers to be creative and to let their curiosity to really produce ideas. And 9 of these ideas may be wrong, à côté de la plaque, as you see in French, but perhaps if one of them is a good one, it will change the world. So history shows that often these major breakthroughs come from this fundamental research. So a couple of examples from that I like to show, to mention from the last centuries. Perhaps the two main breakthroughs of last centuries are quantum mechanics and general relativity. And if you think about them, perhaps there is nothing more far away from everyday life than quantum mechanics and general relativity, simply because they have to do with the microscopic world, so they're very small, and the rules are different than in our world, or the very big, and again, the laws are different. And yet, without quantum mechanics, our modern electronics, all our gadgets, iPhone, iPad, everything, would not exist. They are based on transistors, and so they will not exist. And without relativity, our GPS will not work. They will send us to another wrong path. But I would like to say that most importantly, perhaps, beyond what the applications are, knowledge as the arts are among the highest expression of the human being as clever being. They are the expression of our curiosity, creativity, ingenuity, intelligence, etc. And so they justify themselves by their intrinsic value. I don't have to fund, and I'm not going to give money for a nice museum or a concert thinking that it will bring me economical benefits. I do it because art is something noble and something good and something of which we can be proud. And an Italian poet of the 13th century, Dante Alighieri, you perhaps know him, wrote, nati non foste a vivere come bruti, ma per seguire virtute et conoscenza. You were not born to live like animals, like brute beings, but to pursue virtue and knowledge. And I like to report also more recent quotes by Bob Wilson. Bob Wilson is the founder of Fermi National Accelerator Laboratory. Fermilab is the second largest laboratory in our field after CERN. And so in the early 70s, Fermilab was visited by the US Congress. And one of the congressmen asked Bob Wilson, but tell me, what will your lab contribute to, in which sense and how will your lab contribute to the defense of the US? How? And Bob Wilson replied, in no way, nothing, except to help make the country more worth to be defended. Thank you.
Merci vraiment Fabiola pour cette fantastique présentation.
Many thanks, Fabiola, for this fantastic presentation. We will now open the floor for any questions. So I think we have students with mics in their hands. So raise your hands if you wish to take the floor, and we will try to take as many questions as possible. We'll start from the sides. Yes, sir. Fifth rank. Fifth row.
It's going to be in French or in English, donc n'hésitez absolument pas. Voilà.
Merci.
Thank you. Higgs boson, I believe, has a relatively strong mass. So how come it's hidden? Where does it hide?
Boson energy and mass hide, and is so difficult to discover.
So I'm going to answer in English because I think the translation is from English to French. So the Higgs boson is actually, well, it's a massive particle, but not so heavy. Yeah? It's about 130 times the mass of the proton, 130 times the mass of a hydrogen atom. Here I have to go a little bit in more technical details. The Higgs particle is associated with a field. Every particle, elementary particle, is associated with a field. That, for instance, I don't know, the photon is associated to the electromagnetic field. And actually, the Higgs field is everywhere. It permeates the universe. Otherwise, again, the quarks and the electrons in our body, which get their mass from the interaction with the Higgs field, will not be massive. So the universe we discover with the discovery of the Higgs boson, we also discover that the vacuum is not empty. There is a field, and this is the Higgs field. The Higgs boson can be produced by exciting this field from the collision of, for instance, of proton beams. Okay? So the Higgs field is everywhere, and the particle can be seen as a fluctuation of the field that we produce when we smash high energy beams.
Je crois qu'il y a une question là-haut. Merci. Peut-être vous mettre debout, peut-être, je sais pas.
Qu'est-ce qui se passerait si la...
What would happen if the particle accelerator was to explode?
Ça va pas, je peux t'assurer que ça va pas exploser.
I can assure you it's not going to explode because there are many control systems. It's not going to explode. You can rest assured it won't.
Professor Gianotti, I very much enjoyed your talk. I have a question as a non-physicist. What is the proof that the elementary particles are truly elementary?
Well, it's a very good question. We understand if they are elementary or not from the way in which they interact, essentially. Okay, so for instance, we measure their properties, the way they interact, and from that we can deduce if they are elementary or not. Today, for instance, we think that the Higgs boson is an elementary particle, and actually it behaves like an elementary particle with the experimental precision that we have achieved until now. But, additional measurement with higher precision may indicate that it's not. Similarly for the quarks, we think that they are elementary, but if not, if they are composite, they could give rise to interactions that really can indicate the composite nature. Like for instance, when people made the first experiment with atoms, okay, they thought it was the atoms would not be cut, but then by bombarding the atom saw the deviations of particles and then deduced that the atom was not indivisible, or not elementary, but it contained a nucleus with something with a lot of vacuum around. So similar things clearly translated into even a smaller world are tools that allow us to understand if a particle is elementary or not.
Juste encore, on reste à gauche, mais n'hésitez pas à droite plus tard. Voilà.
Still to the left, but feel free to take the floor.
If you don't mind my adding a point from another famous physicist of old, I used to love to tell my students this. When Michael Faraday had discovered induction, he was later interviewed by the then Prime Minister of Great Britain, and he was asked, this is a really cool stuff, but what is it good for? And his answer, I'm paraphrasing, was, I don't know, sir, but one day you'll be able to tax it.
So one day, perhaps, Switzerland will tax the Higgs boson.
S'il vous plaît, peut-être à droite, là. Voilà, pour moi.
Yes, to the right.
Thank you for your presentation. It's also a question from non-physicists at all. So you said a big thing was like the Higgs boson, but now you found it. So what's next? What is, like, as a curious human being and like many other people here, like we'll wonder what's next in the pipeline? What are you looking for? Is there something specific or?
It's a very good question. So first of all, the Higgs boson is a relatively new friend. We discovered it only a few years ago, and so we know it much less well than the other elementary particles. So we are going to measure it with very, very high precision. And since 2012, a lot of efforts and a lot of progress has been made in pinning down the features of this particle. This is also a very special particle because it can open the door to new physics, to physics beyond the physics that describes the elementary particles we know today. And I hinted before that there must be new particles because we don't understand dark matter. There must be new phenomena, new interactions. We don't understand why the antimatter disappear. So these are the kind of questions we are behind. So we are addressing this question by measuring the known particles, the particles already discovered with very high precision, because every single deviation from what we expect in their behavior may indicate new physics. But also we are looking for new heavy particles. It could be dark matter particle or nature knows what. And we are, of course, our researches are on one hand also a little bit guided by theoretical ideas and theoretical scenarios. So the Higgs boson has been predicted by the theorists I mentioned before. But at the same time, we try to be very open experimentally, because nature may, there are many theoretical scenarios that have been developed, but nature may have chosen something completely different. As I used to say, nature is much more clever, simple, and elegant than the human brain. So we are trying to look everywhere and to explore this new energy scale made available by the Large Hadron Collider and by the technology to address some of the questions I mentioned before.
Thank you. Do you think that we are getting close to the limit of CERN when it comes to reaching higher level of energy, and that it will be necessary to build other machines everywhere in other places, or that there is still a lot of places for the future of the CERN to reach a higher level of energy within this same structure and with the same diameter?
Thank you. I can't really follow all the words of the question because there is a bit of an echo, but if I understand correctly, you ask about higher energy and the future of the discipline at CERN or elsewhere?
The limit of the CERN due to its diameter. Do you think that at one
point... the Large Hadron Collider due to the...
Yes.
Yeah, so it's a very good question. Yeah, okay, so can we go to higher energy? Yes, we can, as Obama said. Yes, we can. What we can do, we are at the moment developing the superconducting magnets of next generation. So if you want to keep the same ring and go to higher energy, as I said before, what is difficult is not to accelerate the protons. We can accelerate them to higher energy, but we need more powerful magnets to keep them in the ring. So using the existing ring, 27 kilometers, we can go to higher energy if we have more powerful magnets. And so now we are developing, and the experts from CERN and all over the world are meeting these 3 days here in Geneva. We are developing new generation magnets based on new materials. So as I mentioned before, this niobium titanium is the superconducting material used for the current magnets. For the future, we are thinking about other materials like niobium tin, for instance. So we think that on a time scale of a few years, we can double the energy in the LHC tunnel. And of course, if you want to go to much higher energy, you have to build a bigger tunnel, because then you can combine not only the power, the bending power of the magnets, but also the fact that the tunnel is bigger, and so you have to, you need less bending power.
Yes, I have a question about the principle you mentioned earlier with the two Ferraris. So you smash them together to analyze what's inside. So if I think about your experiment, and you want more energy, more acceleration to smash protons together, isn't there another principle in particle physics to analyze, like quarks engineering somehow, or other principles?
Or what? Quark engineering, or, sorry?
Another principle when just making a collision and analyzing the chaos which comes out of the collision.
So I'm not sure I understand your question, but clearly one of the ways to study the elementary particles is to use accelerators, okay? It's not the only way, and high energy is not the only way, because there are some phenomena that do not require so much energy, but require very, very high intensity, very high intensity beams. So for instance, if you want to study neutrinos, which are very elusive particles, which interact very weakly with matter, you need really beams of very, very high intensity, relatively low energy, high intensity, and big detectors in order to maximize the probability of the neutrinos to be produced and detected. To study the fundamental law of physics, also in particle physics, there are other ways. You could, for instance, look for, dark matter particle by installing big detectors underground to protect them from cosmic rays, and look for the interaction of this dark matter coming from the intergalactic halo with this detector. So I don't know if it answers your question. High energy accelerator are only one component of our exploration of fundamental physics and particle physics. There are other ways.
Thank you.
Bonsoir. Vous avez mentionné plusieurs éléments.
You've mentioned a number of pieces of work and the answers that CERN could provide, among which dark matter and dark energy. Today, there seems to be several trends within the field of physics which seem to consider that dark matter and dark energy are some sort of illusion which shows the limits of our theories and the Big Bang model. Is this a debate that is going on within CERN, or does the consensus remain?
It's true. So first of all, at CERN we can't do much for dark energy, frankly speaking, except, of course, improving our understanding of fundamental physics or the various fields, and so this also contributes also to the dark energy. We can do something on dark matter if dark matter is made of some classes of particles. Now, there are theories who essentially say that dark matter and dark energy are just modification of gravity and general relativity on large scale. I must say that for what concerns dark matter, I'm a little bit cautious. I don't think that these theories have been able to really explain all the experimental observation. I still like the interpretation that dark matter is something out there made of particles. Perhaps it's not just made of just one type of particles. It could be a spectrum. After all, also in the ordinary matter, the matter we see, there are many elementary particles, so also dark matter could be made of different types of particles. Modifications of gravity for what concerns dark matter, there are many theories like that now. They are quite fashionable. Personally, I'm not so much convinced. But again, I'm an experimentalist, so for me, what is important is the observation. So we are going to do the experiments, not only at CERN, but also in other approaches, and then we will see.
Tout au fond, et puis ensuite peut-être devant. Tout au fond d'abord.
So I have a less technical question. You started by saying that every European citizen contributes with 1 cappuccino on average to CERN, to the research. So do you think it's reasonable to maintain that 1 cappuccino in the near future, or maybe making it 2 or 3? Do you think it's reasonable to achieve?
I think we have to double. 2 cappuccinos per year would be okay.
So do you think it's...
Sorry. No, seriously, the CERN budget you see is a budget of a good university in Switzerland. And you see that this budget is invested for advancing fundamental knowledge, and at the same time I try to list also all the other benefits in terms of technology, in terms of education, in terms of peaceful collaboration, and these are things that they have no price tag. Peaceful collaboration, bringing people together, make them work together regardless of their ethnicity, political ideas, beliefs, for me is really something that should be pursued in many, many places in the world, and unfortunately there are not so many. So these are things that we cannot do.
Du boson de Higgs est mentionné.
Regarding the Higgs boson, have you tried to study the metastable quality of the Higgs boson in vacuum, in a vacuum, as well as the evanescent particles that Professor Carters has mentioned? with extremely high levels of energy, such as the energy that can be created by the LHC, it could be possible to have an effect on the vacuum of the tunnel. I'm sorry if my question is a bit tricky.
Vous avez posé plusieurs questions dans votre...
You've asked several questions at the same time. I'm not sure I've caught everything. I'll try to discuss them in turn. So the...
It's from English. So the mass, the mass of the Higgs boson is actually relatively light. Comment? 125 GeV. So the mass of the Higgs boson is indeed quite light, and in the theory that describes the particle interaction that we know today, called the Standard Model, this mass, it's not protected, how to say. This mass tends to become very, very large, and there is a mechanism of compensation that it keeps relatively light. So the fact that we observed a light Higgs boson is a bit of a puzzle, because without additional new physics and other particles that help the mass of the Higgs boson to remain low, people have discussed about supersymmetry and other theories, this mass tends to diverge. So this is one problem, which for the moment to which we have no answer. The other problems to which you mentioned is the vacuum stability or metastability. So it's a complicated thing, but based on the mass of some of the elementary particles, including the top quark and including the Higgs boson, it looks like our universe lives in a metastable state. So our vacuum, the environment in which we are, is not stable, and some point we are going to switch, to basculer, as you say in French, to transit, in another vacuum state. Don't worry, the lifetime on which this is going to happen is at least the lifetime of the universe, 14 billion years. So we are safe, because we will not be there. So, but again, knowing if the vacuum is stable or not metastable depends exactly on the values of the masses of these particles that now we are trying to measure with very high precision, and also, of course, confront with the theory. So it's interesting. It's something that we are... And then there was another question. No, that's what was it? Okay, I don't know. In case you come back.
Ah, je crois qu'il y a une importante question tout là-haut, un jeune avec un blouson vert.
What would happen if there was a person inside the machine?
It would not be nice for the person. So and we try to, even the people we don't like, we try to keep them out of the machine. Yes. So essentially it's impossible, even if you wanted to have some nasty person that we really hate to be inside the machine, we can't, because the machine is really protected with a very, very sophisticated set of controls called interlocks that really prevents people from remaining inside while the machine works. Of course, when it is switched off, there is no problem. You can walk in the tunnel, you can bike in the tunnel, there is no problem.
Écoutez, on a eu énormément de chance, je crois, vraiment, d'avoir autant de temps de la part de Fabiola Gianotti, vraiment, non seulement pour nous exposer vraiment ces très belles réalisations au CERN, et surtout aussi pour cette excellente, vraiment, session de questions et de réponses. Vraiment, encore une fois, je vous prie de vous joindre à moi pour féliciter Fabiola Gianotti. Merci pour votre présence.